Okay, let's start. So in the first half, 2 hours, we covered how to do the raw spectral processing, LS and LC-MS1 and MS-MS. And basically this process will generate a table and peak abundance table. So this table can be used for statistical analysis, functional analysis. And so this second part, that's next 2 hours, we are going to introduce how to do data processing, statistical analysis, and from this table. And this the input of a table can be the peak intensity table or the target like a compound concentration table. And also we are going to cover the last part is called the causal analysis. We are going to introduce you how to do you perform Mendelian randomization, and this must be from targeted metabolomics. You need to know the metabolite ID to see whether metabolites associate with these phenotypes, whether it's causal or not. Okay. So this is 3 modules we are going to cover in this session. And in the first 2 hours, we covered the top 3, spectral processing, LC, MS1, MS2, and functional. Now we're going to cover 3. All the remaining, we do have the tutorial PDF slides. You just go to MetaboAnalyst, go to the tutorial, you'll see the remaining. But here we just focus on 3 on the first half, and these 3 on the second. So here you see we're talking about raw spectral processing. It's really, in this figure, we cover the data pre-processing, and we need to centroid the spectra. We need to do LC, MS1 peaking alignment, and MS2 deconvolution and compound identification. Now we talk about the remaining is peak data processing. From this table, we need to do quality checking, missing value imputation, data filtering, normalization, then do a stats and PCA, PLSDA, maybe classification. And enrichment analysis we are not going to cover this time just because we already covered the previous one. It's relatively straightforward if you're doing a target analysis. But we are going to talk about choral analysis. So this is slightly integrating with the genomics data. Okay. So data processing, and we need to really have in your mind, there's pictures, what the data looks like. The data is a table, and with compounds or peaks in the rows or in the column. So it can be either way, but you need to be aware of what it is. So it's a long table. As a long table means have more columns, very long. Wide table, this have more columns. Or if it's a long table, it means very long. It's especially for the target on-target metabolomics. You have more. Each feature is actually in a row and samples in a column. So overall, is you can save your data in either way based on your habit, but you need to make sure that tell the program here which samples in a row, samples in a column. So on target metabolomics, because we have a lot of features, usually you don't want to make it very wide. And you don't want to just scroll. You actually make it very long. So usually it's peaks in each row and the samples in the column. So it's usually like this. And of course, for this table, you can also have the NMR spectral bin. So basically, you don't need to align. You just bin in all of the features and put it there. And here's another actual thing I mentioned earlier. If we doing clinical studies, or exposome studies, or some observational studies, you don't have a clear control about factors, and you have to include a lot of other factors because the experiment, you can control everything the same. Okay, the only difference is your experimental condition. You have control, you have disease, or you have time point 1, time point 2, 3, 4. And this is the only experimental factor you are interested in. But in observational study, in the clinical or other studies, you have no control. And the only way is including all these factors into your study design and upload this as a table, because in this case, you really need to provide a separate table. In addition to metabolomic data, you need to have a metadata table. And here we show a table shows about COVID. This is for human. So we cannot control other factors, but we included them. And these factors help us to decide what's the best strategy to analyzing the data. In this case, you see the sample ID and its first column. And the second column you see it is primary interest. So it is COVID or healthy control. And the other factors you see is gender, and other factors treatment and age. So some studies you can have more than 20 or even 15 metadata. This is common, okay, because you don't know whether it's important or not. You can include them to be uploaded. You will later find out that some factor is important, some is not. And some factor you must consider during analysis. Some you can safely ignore. So, but this one is important in clinical study. When you're doing a human study, this part you just quite natural, you include it. And the thing is that when you have this metadata, and it became tricky, and because tools actually, our tools initially designed to analyzing a numerical matrix, like doing stats, like metabolomics and transcriptomics. But when you're doing a metadata, it is very descriptive. Some people just write some note, a clinical doctor writes a note, and they are not necessarily very consistent. And when you upload, you need to manually tell the computer, this is categorical, basically it's group 1, 2, 3. This is continuous, this is like age, blood pressure. So the computer can guess, but not 100% accurate. So you need to make sure you double check after upload the data. With a metadata table, you want to have a table, metadata table. This MetaboAnalyst is going to show you a table and summarize it. You need to really just go through it, see whether it's right or not. The computer can guess, but sometimes they make mistakes. And if it's wrong, you need to correct it. Also, currently we do not allow you to have missing values in the metadata table. Why? Is because you know the best. If you're missing, you do not want the computer to guess. You better guess yourself. So you try the best to fill that missing value. So numerically, with metabolomics or even transcriptomics, we can impute, we can guess. But metadata, we leave to you. Okay, it's not the computer cannot do it. It's just really we don't feel comfortable let the computer do it. So before you upload, make sure you give a full metadata. Even something missing, you need to fill that first. And for that one, you actually can view and edit. So it's really, you can think about this Excel, but it's not like a full functional Excel. You upload, you can see it, double click, you can edit it. Otherwise, you won't be able to go to the next step. So really, if you upload a high quality, it's all fine, but if something is wrong, you can manually click, edit it. The other part, you see that it's not editing it, change the values, it's changing the orders. Sometimes people want to plotting and actually high, medium, and low. And the computer not necessarily knows the order, okay? You read it, high, medium, low. If computer default is H, L, M, high, low, medium, because computer default will do the alphabetical order. If you think this is a meaningful order, you need to reorder it and see this is order important and click submit. Then computer will remember, oh, this order actually meaningful. When they're doing the computing and plotting, they will recognize, respect your order. So this part is people complain, why computer don't do it? Because computer does not know that order matters. So all you need to know is that order it and save it, and the computer will respect it. And that's metadata. It's actually it's a new features for the version 6, really recent one, just because we do a lot of exposomics. Exposomics contains a lot of metadata. And now let's go back to the omics data, the metabolomic data. Metabolomic data contains a lot of noise, okay? Especially on-target metabolomics data. We need to do feature filtering. And this is very important. People said, I want to include everything. And I understand that concern, but you have to understand that metabolomics or omics mirror everything, and they contain a lot of noise. And you have a lot of noise, you actually dilute your signal. And the best way is you do some filtering. This filtering will enhance your signal, improve your power. And here the picture shows that most of the time we do omics data, we assume the majority is stable, okay? They have the homeostasis, they are stable. The changes are minority, let's say 10%, not more than 20%, okay? We're talking about minority changes, majority background remain stable. If they are stable, their background, you can filter in certain part of it and without hurt anything. So one of the most important things is that if it doesn't change a constant background, it does not contribute to the biomarkers, so you can filter them. In transcriptomics, and I read some recommendations, they almost telling you can filter in 15%, almost half of the genes without hurting your result. That's almost quite established. So metabolomics, you should also have a certain kind of practice. Try to reduce uninformative features. Some people really want to include everything. This mindset actually not good for omics data analysis. And so I'm just giving you something is that filtering is important, especially for on-target metabolomics. So how do we filter in data? The most important thing is that when you're filtering data, you should not use any information from the primary experimental factor, if you use that into consideration, you're damaging your result, you bias your result. But what's the criteria? We have 3 common criteria. And the first one is the low quality data or low reliability data filter. And how do we filter that? Is if you have your QC samples and you repeatedly inject your QC samples into a machine, and this is technical replicates, and it's supposed to be very stable, it does not change. So if it changes a lot, that means you cannot mirror these features reliably because it's technical replicates. If you change it a lot, that means they are not reliable. You should filter them out. So you just use some variance filter. If you have very high variance for this based on QC samples, you just filter them out. So this is low quality or low repeatability filter. The other one is low abundance filter. If you think about our machine, they measure certain ranges, best quality is really best at it. If it's really close to baseline, they're not very good at it. So sometimes low abundance, you can remove it because very close to baseline. And the last part, everybody understand, low variance. If it doesn't change, then it contributes too much to the conditions of, does not relate to condition of interest. You can also filter them out. So overall, that this is well established, and it helps you remove the features that's unlikely to be informative. And you can remove 10%, 20%, even up to 14%. And the result should actually improve. So this is something people don't feel comfortable, but omics data really contain a lot of noise. Filtering helps a lot. Normalization is also quite common. I think most of you actually accept that normalization is critical, is important. And there's no single best normalization suitable for all your data. So it's more or less depending how your data looks like. You need to try a few. But at the beginning, you should try the simple first. So one of the one you usually doing is sample-wise normalization. This is if your sample is come from different volume, different mass, you need to normalize them. This is before you upload. You should have a based on mass, based on volume. Sometimes you don't know, just based on total sum of the signal. And this is all fine. For example, if you have urines, have stuff, you have dilution factors, you can actually use the total sum to normalize it. This is sample-wise normalization. It's really based on more biological normalization, so it's making some sense. And then there's data transformation. Data transformation, like a log transformation, really apply independently to each of your data point, which is actually quite common and quite useful. And most of our concentration abundance is log normal. If you apply log and become naturally close to normal. So try log, always try log. Unless you already log, so you don't need to do it. But otherwise, log normalization is you should try the first. Also, we can easily understand log because that's really just dependent on the value itself. It does not depend on other things. So the other last one is data scaling. So data scaling, for example, unit scaling, a z-score. After you do the scaling, you basically have the mean 0, standard deviation 1. And this makes it very comparable across. But this step also increases the signal. Increase the noise, could potentially increase noise. Also, it could be hard to understand just because the scaling is considering not only the value itself of this current value, it's also considered the whole feature, whole column. Everybody else, they consider as a normalizing factor. They subtract the mean divided by the whole range of things. So it's really make the interpretation slightly harder, okay? And just because they consider the whole group, whole column, or whole rows. And log is usually very straightforward. You can actually, I get a value, I can go back to the original value, but you cannot do it with scaling because scaling is not based on this particular value. It's based on all the column, everything else it related to. So overall is that you can try, but do not, at the beginning, you try the most fancy ones that I apply log, then I also apply median scaling, then I apply the auto scaling, and try the best to make the data look normal. It will make it very hard to interpret later. So do it cautiously from simple and gradually increase if it have to be like that. So here it just shows something. You can have very dramatic effect on the data. You can actually really torture your data, get it looks normal, but it's not necessarily good for your long-term, especially you want to reproduce it in a next round of large-scale studies. The minimal normalization will make your data more robust. Too much manipulated data make it very hard to reproduce, hard to understand. So this is something is simple is first, and probably just doing a log. That's my recommendation. And the other thing is just only you can justify it. So this is something you can look at it. Also the normal distributing the Gaussian shape. It's not necessarily means they are truly Gaussian because a high-dimensional Gaussian is very hard to guarantee. It's almost impossible. And all you see is just probably improved, but it's not necessarily globally normal. Okay, high-dimensional normality definition is very strict, and here we just cannot guarantee it is. Okay. Now assume we tried our best and clean our data, filtering some uninformative features, and normalize it, and now it's ready to do stats. So the main issues for stats is help us filtering or sifting through the features and find those that more we can focus on because we still have thousands of peaks or many compounds, and we want to identify those that most relevant, most interesting. So always starting with the very simple ones, t-test, fold change, ANOVA, plus post-hoc is very, very useful. Not because it's simple, it's not good. Actually simple, they are very useful. Always starting from that. Most of the times when I do this simple test, I develop a story and confirmed with PCA later. It's really helping a lot to think because we are comfortable when you use the simple method, you're focusing on the data, understanding. If you use very complex, you actually think about what the method means. You focus on the method itself as distracting. So simple ones actually help you focus on data, starting developing your story. So here I would like to introduce one is called linear modeling. It's Lemma. Lemma is a very common method used for microarray data analysis, which is much more flexible. The reason I introduced this is because it can deal with multiple factors, covariant, and time series. So it's almost anything you in your mind, it actually can deal with that and very fast. And if you compare lemma to t-test, lemma can do everything t-test can do and can do a lot more. Okay. So dealing with covariant. So if we have excuse me, very complex metadata, and how do we deal with that? The thing is that do not try to include in everything. And clearly, when you include everything there, and some of them will have to have damaging effect. So you only want to include them that's necessary. How do we know it's necessary? And there are several ways. First is that if you do an experimental design, you are the PI and you do it, you can try to control it. It's matched, it's actually comparable as reduce these unrelated things as much as possible. But if you are the data scientist and you already get the data, and what you can do, if you have a lot of samples, and you can try to match based on age, based on the gender, and there are several things. It's very clear. Is that first is try to reduce it. You have a lot of the metadata. You can actually use PCA plus heat map and see a lot of metadata is highly correlated, and you can clearly see it. They are correlated, and they contains redundant information. In that case, you just need to include one of these metadata. You do not need to include multiple ones because they are telling the same story. Actually, if you have very correlated metadata, some stats will fail just because they are collinear. And then the other one, stratification, is that if you have a lot of data, you can separate the male analysis, female doing analysis. So you just separate it based on those age group, based on the gender. So you can do it. It's not, but assume you have a reasonable amount of the data, you can stratify them. And the other ones, taking them into account. Basically, this is a covariant, and they can adjust them. So the lemma can naturally do that. So here just shows, I mentioned earlier about t-test versus a linear regression. So linear regression basically introduces actual values to naturally absorb these different factors, covariant. So in this case, we just consider the slope, this slope, which actually is your main interest. And everything else, if you introduce the new factors, it will be absorbed by this. So linear regression actually is definitely everything t-test can be doing it. You can use linear regression. So here just shows if we use multiple factors, how a linear regression does this. It can naturally consider this is your diagnosis and it's your age, so it will naturally absorb that, take that into consideration. And you can actually test how significant or not using this coefficient estimation. And so overall is that this is very well established. It's just people didn't custom use it, but it's actually quite robust and well used in transcriptomics, and almost all RNA-seq is based on more or less this linear regression. And the thing that if you use linear regression, you include in this predictors, which is actually your factors. If highly correlated, it will give you some errors. So it's rare, but it's common. When it occurs, it's quite frustrating. Why is it like that? I receive people's forum post and ask, then can you give me your data? Then I say that, okay. And then you have collinear data. So in that case, how we identify them, so we actually need to do one step is using overview of the metadata, and some of the metadata is highly correlated. You don't need to provide both. So in MetaboAnalyst, we have two statistical modules. One is a single factor, and this is the result. This is a method overview. We have about 15 or 18 different methods. And the other one is multi-factor study design. So you have omics data and plus an actual metadata table. And in that case, we have selected a few methods, probably 8 methods, that are more suitable, can take into consideration of multiple factors. And you have more method here because it's simple, but this is more selective. Now here I shows how you identify the metadata that's actually highly correlated, and you can safely ignore some of them. And you only also help you identify metadata that actually related to your omics data. Some of metadata is there, but it seems does not correlate with your data. You can ignore them because you included them, you just consume some of the your power, okay? So how do we do that? Is actually this is purely empirical. You just visualize them. Two of the best visualization approaches, heat map and the PCA. So you just classed in this metadata and just to see how they are similar to each other. And because all the metadata, the value can be converted to numerically, and with different color code, you can actually see them. If they're similar, and they will be similar to each other. And so this is, I showed you in COVID data, and actually some of them you can see is highly correlated. And if you really see that diagnosis and treatment is highly correlated, clearly you have diagnosis and you give the treatment, and they are similar. It's not surprising at all. And for the PCA, you actually can use PCA to see some of the metadata. Actually, when you're coloring your PCA, which is PCA is based on your metabolomic data, but you can always color your metabolomic data with different metadata factors. When the metadata color shows on the PCA have some clustering patterns, you know this metadata have some effect on your PCA. So this metadata should be included. If the metadata have almost no correlations, random, then probably you can ignore them. So overall, there's no strict rules, but there's always something to help you to make a decisions. If you have 20 metadata, you have to reduce them, like reduce to like 3 or 5. You do not want to include all of them. And the PCA and the heat map help you to filter them out, identify those that are related to your metabolomic data. And here is that shows if you use Lima linear modeling and you upload the data, you can see the bottom going to have these factors, and potentially you can include as covariant. And the top one is always your most primary one, is diagnosis. And here's your available metadata, and age, gender, or other factors. And then it will do the analysis and show you the result, and basically compare those with covariant adjustment, without covariant adjustment. You can see there's changes. Some of the significant features will disappear, some new signal will come up. This is natural because that covariant actually have an impact. And sometimes it's dramatic. You suddenly realize, oh, this gender effect is so strong and it's biased. After you adjust it, suddenly you have much less significant features, which is actually a good thing. And we have recently published a paper in a very high-profile journal, and then we found out this, I think, gender-related effect. And once you adjust for that, there's quite a big change of the result. So there's another parameter is called a fixed effect versus a random effect. And most of you are not a statistician. I'm a user, so I spend a lot of time and try to understand what's the fixed, what's the random. But I don't want to bother you too much with it. But I want to tell you is that disregarding how people think a random effect seems more fancy, give you more power. If the reality is fixed effect is slightly more conservative, but it's robust. It usually do not give you errors. If you use random effect, sometimes you will have some issues. But the fixed effect is efficient and slightly conservative. And the effect you identify when you choose the fixed effect, almost more likely to be real. So I read a lot, and just let you know is that the people just fixed with certain things. But here is that you just use a default. Default is fixed effect, covariant, and works very well, and most time it's doing well if you are not really want to understand the difference. And the only thing I found it useful is the subject time series or batch, and if you match them balanced, you can use it. But most time you just treat it as a fixed, because that's a safe choice. So here we'll show you that how do you interpret the result, and the result actually tell you what's significant, those keep significant, those actually change after you adjust. And you can actually click each of the data point and see what's the change. When you see that coloring, and sometimes there are changes just so significant associated with the covariant, and you feel more meaningful because they changes when you adjust for that, and it is quite interpretable when you compare before and after. So that's univariate, but considering covariant, basically primary diagnosis disease and plus some gender, like age, and you can use in linear modeling. Now we just go briefly to multivariate. Multivariate is we consider all of them together. Okay, the most commonly classical one is PCA. So assume all of you have an intuitive understanding of PCA, and PCA is so useful. Okay, it is try to identify this low-dimensional space and capture the most variance of your data. Okay, it's really good for overview, and you can identify outliers, and also you can color them with different metadata and see how metadata associated with your omics data. So this is very good for exploratory data analysis. And the PCA is really have an assumption. The most variance of your data is your interest. This most time is true, and we do expect our main factor, external factor, have a large effect on your data. But this is most time true if we're doing experiment, because we treat it with different drugs and it cause a different change. But if you see some disease, some subtle conditions, this may not be true, okay? The most important changes could be your batch effect, could be gender, and your disease or something else, actually second factor, third factor. So it's not necessarily the first, the condition not necessarily cause the biggest change in your data. But this is quite useful for you to understand how PCA works. And PCA is very good at summarizing. You can see if we do hundreds of the bins or peaks, you can summarize into 2 dimensions. And if it's happening to separate very well, that means your experimental factor actually caused a huge changes in the data and captured it in its first 2 dimensions. And you see the separation in the PCA, you almost can write your manuscript because PCA is unsupervised. And if the separation is there and it's real, okay, you do not need to worry too much about overfit. And how PCA works and the linear transformation, and so it's very interpretable because the linear, you can almost link in the features to the separations, okay? So that's, I don't want to tell very details, but you just keep it as linear relationship. Once the linear, and you can link to the separation, tracing back to the underlying driving features, which feature contribute to the separation, right? So here we just shows the PCA, how intuitively interpreted the scores and the loadings. So the left side is score, and you see the samples there, and separating very well on the green, blue, purple, and red. So on the right-hand side, it is loading. So each of the loading and corresponding to each of the score. So the loading on the same dimension, same direction, will positively correlated the samples here. So the samples is here and loading here, they will have the highest abundance. And in this group, these samples have the highest abundance in these features. this feature is most abundant in this group. And this, for example, here, this purple, this feature have the lowest abundance. This is negatively correlated. But this group will be positively correlated with features here, just because they are linear relationship. So it's really intuitive. You can actually, in MetaboAnalyst, you can actually click each dot, can see whether it's true or not. You will see, oh, here, actually everything here is high, everything here is low, just because the computing and the mathematics determine this must be like this, okay? And PCA is unsupervised. That means it does not consider your group information, okay? So if PCA separates your data corresponding to your group information already, you are lucky. That means your group actually caused, or your treatment actually caused a huge change in your data. It's just overlap, give the largest of change. But when this is not the case, you need to use a supervised approach. Supervised approach commonly used the PLSDA. So PLSDA is supervised. The difference is they found the covariance in your data, omics data, that's maximize the separation of the Y. So basically it's maximize the covariance between X and Y. And because of this supervised guiding to the algorithm, PLSD always give a separation or better than PCA, so it's guaranteed. And so this is something you're not surprised just because it's just designed to behave like this. And here you just need to just be very clear about what's the difference between PCA and PLSDA is variance and covariance. So in this figure, you see this variance is basically this changes most. In this case, it's because it's slightly longer, so the change most is around this direction. So it's diagonal from the top left to the bottom right. This one is have the length is the most changing a lot. So if with the PCA1 will capture this one because it's very most variance is here. But if you talk about the maximum covariance, it is this one. Just you can see the two groups, red and blue. This is the maximum covariance. In this case, the first component in PLSDA will be this direction, okay? But in PCA will always be this direction. So this is difference between variance and covariance, just illustrate what they're aiming for. So PLSDA will find the things that maximize the covariance, the direction that maximize covariance between the groups. And in this time, the two groups, blue and red, is this direction. So this direction, okay? And it's different from that. So this one will illustrating things like this. And in MetaboAnalyst, we give you this called the pairwise score plot, and for PLSDA. And sometimes this rank is based on the explained variance in the X. Okay, they are not necessarily. This is so this this here. You see this? So the fourth component actually explain more variance, but they are not ranked at the top, right? Because they are not the top one always the maximize the covariance. Okay, this one shows the variance captured. It's more variance, but this is one just shows. Don't be confused because this is ranked by the covariance. So the first component always capture the most covariance, and the number here is explain the variance. Okay, that's different. So the other part is using PLSDA. Always there's extra layers of complexity. It's a supervised method, and have the risk of overfitting. Overfitting is really the danger of the irreproducible result. A lot of times we found the patterns we want to test on new samples is not true. Why? Is because the sample is not, it's overfitting, let's say that. So what's overfitting means your sample is working very good on your current data. It's not working as good in the future data. And there's bias. So how do we get more objective evaluation of this, your performance? And we need to do actual layer, okay? Overfitting is basically you fit very well, but you actually fit a noise. And this is something just illustrated. The best ones here, and here's the underfitting. You're probably too conservative. You're saying this, oh, the performance 70%, but here actually 18%. But here's 90% is overfitting. It's probably you're fitting noise. So addressing the overfitting in PLSDA, there's two approaches in MetaboAnalyst. One is cross-validation. So I don't want to mention more. It's basically you divide your sample into different portions. Some for training, some for testing. So we rotated 3 times for 3-fold cross-validation, or 10-fold cross-validation is just divided into 10 times. And so it will give you some values more objective than just use the whole data as a training. The other part is permutation test. Permutation test is basically you shuffle the group label and redo the analysis and compare the analysis versus use original label. So for the cross-validation, PLSD give you some result, classification accuracies, or R-square, Q-square. R-square, Q-square is based on the regression, because PLSD actually is a regression approach. So you can just use R-square, Q-square actually based on the regression. And Q-square is more like a cross-validated approach. And you can see sometimes Q-square is really can be negative, so that means not predictive at all. So anyway, I personally don't like this approach, and just because it's very traditional, people always want to use it. But it's sometimes you see the mathematical formula. It can be improved, but it's so established. People always want to use it, so we provided them. But if you want to know more, just go to see this text below. You will find more. So here's the permutation. Permutation is that in MetaboAnalyst is we just found the distance, separation distance between two groups using original. And here's the green and the red. And you permute it and try to calculate their distance using PLSDA. If the original one always good than the permutated, that means your original one contains some signals that have been captured by the model, and potentially it's valid model. So here is that you plot that separation based on original and versus all the permutated, and you can see how good they are. If it's always good, it's definitely that's significant. Okay, we can do a permutation test and give you a p-values of that. So the p-value is just if you permute it 1,000 times, only once. Always only once is good, so it's almost 1 out of 1,000. So it's very significant. So you cannot never get a 0 because because permutation always you can never infinity, right? So but you can always see p-value is less than 1 out of 1,000, because within 1,000 you never get any values better than yours. So you can p-value less than 1 out of 1,000. You can always safe to see that. And the other part is the group ordering. So people sometimes is complaining about, hey Jeff, I changed the group name from 1 to 3 to high, low, medium, and the pattern looks different. So why it's different is I mentioned earlier, PLSDA is a regression. They convert your label into numerical values. So if 1 to 1,000 and 1 to 2, and for us, it's more or less, these two groups. But PCA will try to adjust the difference, just 1 to 1,000, 1 and 2. You know, the numerical change will be slightly different. So the separation looks better or less. So this is purely visual. Okay, this is purely visual, and it does not affect in actual classification performance. But visually, it looks a huge difference. How do we address that? Is we use matrix and basically use encoding, like current and more latest machine learning AI to address the effect. So if you have a class label that matters, and you time series or something high, low, medium, you just click this, it will respect this, okay? Order matters. If it does not, and just uncheck it, so it will more reproducible. So overall, this is something associated with regression, which I don't quite like it, but just stuck. People want to use it in certain ways, so we try to accommodating. Also, just let you know there's small tricks. Just make sure if you are, do not be surprised with those artifacts, purely artifacts by the algorithm. So let's go to the last one. So at the moment, do you have questions? Feel free to ask questions, because this one, if I'm discussing, is very different from all the previous one.
Hi. I have a question. So going back to the normalization and the transformation of the data, what do you do when those normalizations and transformations have a lot of NAs? Do you impute those data when it's sufficient enough on the data set? And then going forward with that, how do you do the PCA analysis and when you also have imputed data together, if you do that?
Sorry, you said
So two questions. Transformation of the data. Do you do it? Do you impute the data? Do you transform just the data that you have? How do you do when metabolites are close to the limit of detection, and then you do have some samples that have that data and other samples that were not past the limit of detection? Do you impute that?
So before we doing a normalization or transformation, there's step. Missing value imputation. We do that. So I just unfortunately I didn't cover, but 之前 we'll do a demo, okay? We'll show you. We have almost 12 different missing value imputation methods to help get data ready before doing a transformation. And default, if you don't do it, it will try to replace with that detection limit. So if you know something better, we would like to probably address that.
But then also, did you check how the imputed data versus the non-imputed data set changes when you look into the PCA and the linear regressions and so on, and really the statistical analysis?
Yeah, I think if you have a larger percent of the data point are missing, like say 20%, and using imputed, and compare with those, how to say, if you have the imputation, missing value imputation, have a long list of the options, and if you do that and compare with different missing value imputation, and I'm pretty sure PCA will look different, right? So, but the issue is that which one is the ground truth, right? And I do think metabolomics field lacking such comprehensive benchmarking. So I always intended, should I do it? But we never found the time to do it. Overall, is try to do much less with your imputation, because that one, I know how to say, transcriptomics. They have more or less established metabolomics and just don't feel strongly about any particular method that's better. So I have a hypothesis before I doing it. So far that I leave you to suggest me. If you have something in your mind that clearly making sense, I will add it there.
Sure. I think we can talk about that. Thank you.
Thank you for a nice walkthrough. With the permutation test you mentioned, do you do the Euclidean distance and why? Because I think using the just a normal accuracy or area under curve would be much easier for the algorithm. And also I have one more.
No, yeah. Wait, can you repeat again this question?
For the permutation test, you mentioned that you use distance between the groups. I think that could be more vulnerable to false positive, and also I think it would be much more computationally extensive if you use just simple accuracies and AOC. Wouldn't that be sufficient to do the and also when you do the PLSDA, do you use any in-house algorithm, or do you use support from other well-defined packages? Because they tend to give different results. Yeah.
Yeah, very good question. So I fully agree. And for a PLSDA, we do the permutation. Default is based on the group distance, and just between group and within group. And this is well established for the ANOVA, so we just use that. But we also give you a accuracy. Okay, accuracy, how many times you error rate. So clearly you can tick off, I choose accuracy, I choose distance. And of course we can do the ROC based, no problem with that. It's all fine. So I just do not find a strong reasons to really just do this, not that. So far they give you a distance based and accuracy based. And ROC based is clearly doable, and I'm just not sure one of them should be more than enough. And regarding to PLSDA is we use the very basic R function, the base R function they call the PLS. It started from as early as R 2.0, so we use it and we build our PLSDA around it, and we compared with a lot of the other well-established, more or less seems the same result. And I do agree with you. I noticed somebody else getting some different things and get some slightly different result. And I'm aware of that, but our code is freely available. We based on very simple our core functions. So feel free if you think there's something better, and we will consider that. But other than that, we really build organically and use the most basic fundamental ones to build this PLSDA. Okay. It's not a package, it's just the really base stuff. I know, so for example, Mixomics, they have a PLSDA, and, but they have certain functions that are already pre-built in, and it's interfere with our prior normalization. So we know we can reproduce, but it's also cause some constraints, so we should just leave to you. Yeah. Okay, if no more questions, I'm going to the next one. Yeah. Okay. So you can see there's a lot of the small things, habits, each field very specific. For me, is I'm doing a lot of other omics. I'm trying to bring insight learned from other omics, especially transcriptomics, to metabolomics, because that field is actually about 5 to 10, 8 years ahead of us, and they are well established, especially in terms of statistics. So we try to use them. And Lima is one of them. When we use Lima, we found out, whoa, this is really making sense. We just start offering them and recommend that. And this is another one. It's called the Causal analysis. It's actually developed from the genetics field. And, this is probably developed in parallel to metabolomics in the last 10 years. and they focus on the SNPs, and the SNPs our mutations or variant, genetic variant that link to different phenotypes. Some people are more susceptible to certain cancers. Some people are more susceptible to certain diabetes. So this kind of the GWAS, genome-wide association studies, is well established. We have thousands of studies across the world, and that kind of useful. And how we can leverage that information to understanding metabolomics. And this is our last few years we studied into this. So one of the key part is MGWAS. So MGWAS is actually linking metabolites or metabolite concentrations to the phenotypes. And a lot of metabolites, for example, in the blood, urine, are linking to certain like kidney disease and diabetes. Now we have two sets of the things, SNPs to disease, metabolites to disease. And can we integrate them to help us answer some questions that's very hard to answer? And this approach is actually called Causal analysis, and use approach called Mendelian randomization. So this one is offered at the bottom, and most recently, and we also had some troubles because it used a public database, and from OpenGWAS, it's hosted in, I think it's hosted in UK, and they suddenly changed the API in last month, and we have to reconfigure to make it working, and so it was a bit of change, but it should be all working. So how do we detect Causal effects? What's the concept behind it? And the thing is that we cannot modify our genetics usually, and so if we have certain genetics and it linked to disease, and we know more or less these genetics potentially Causal related to that, so we are more or less established on that side. And if here is that thinking, if metabolites or biomarkers is causally associated with disease, and the genetics actually can influence the level of these biomarkers and metabolites. And so this genetics, higher genetics link into like high degrees, the high risk of disease. So you can see this reasoning is very reasonable, right? So if metabolites is causal for a disease, then this genetic variant which influence the levels of this biomarker should result in a higher risk of disease, right? This is very intuitive. Once you accept this, then we can do the computing and tell us how strong it is related. And especially, we have a lot of studies that already there telling you the genetics strong link with phenotypes. The GWAS study is really the last 10 years tremendous. MGWAS is very recently. And we can evaluate this association using Mendelian randomization. Okay, here is Mendelian randomization. The concept is nature's randomized control trials. And basically, you have two groups, like one is with mutation, one is wild type. And the mutation associated with this phenotype, wild type associated with the phenotype. You see there's a natural stratification. Once you have large population, you have all this possible experiment already going on. And you just need to find them from this public database and see wild type versus the mutation, how they associate, what's p-values. So we can clearly do that. Now, if we do that, and now if we put it in this context, is that the GWAS is directly linking the SNPs to the phenotypes. Okay, and I mentioned about MGWAS. We have MGWAS recently. We can directly link this metabolites to the phenotypes. Now this MGWAS. So if genetics influence the phenotype only through metabolites, okay, this is assumption of the Mendelian randomization. It must be linear, only through these metabolites. So if this one is strongly associated with this one, and this one's also linked to that one, and then this line of reasoning will be established. So there shouldn't be a co-founder that affected both of this result. So if you read Mendelian randomization, there's a huge amount of literature. And so, yes, sorry for that. And if you really want to get to the bottom, you need to read a lot. But overall, that the reasoning is intuitive. You need to just accept this. If genomics, mutations influence metabolites only through the metabolites, through the phenotype only through the metabolites, then we can calculate the p-values in each step, and we can know this chiral link, how chirally they are. And the good thing is that there's a lot of GWAS studies, and traditionally require both GWAS and mGWAS to be in the same cohort. But this is very hard, okay? Just because mGWAS only recently. But there's two-sample MR. As they recently, about 2015, they started two-sample MR. They allow you to actually do the computing using two samples. So the X and Y, basically here and here, you can have two different samples and still computing it. So it's really, it's give the possibility to directly evaluate a chiral link. So to do that, we need to collect mGWAS. Okay, GWAS is well established. mGWAS is not, and we are going to have a plenary talk from Claudia. It's Thursday on the mGWAS, and a lot of the studies actually from her group. So this started showing up. So once we have the mGWAS studies, and we have these links. So. We actually collecting all these currently available 65 mGWAS studies, and so they shows how much link the phenotypes and between the metabolites and the phenotypes, and they are collecting in a different instrument, and you can actually see how they linked. And if you're interested if you go there, you can actually find a lot if you're interested in mGWAS. And based on the link between the GWAS and mGWAS, the p-values stuff, you can calculate how strong they are. And here's the p-values and some diagnostic plot, and allow you to give some assessment how strongly they are. Overall, that the p-value from GWAS and GWAS, they need to be really follow this reasoning. So here is that integration, and we actually found about chiral association analysis between about 4,000 metabolites, including a lot of peaks, and with about 200 of the phenotypes. And live demo. So before we go live demo, questions on the chiral analysis? I think it's relatively new, but overall it's coming, because I see even this metabolomics conference, we started to introduce mGWAS, and in terms of integration between the genomics and metabolomics, it's really making sense. So with more mGWAS, and we should be able to put them together and do it. And Ziqiang, you want to do a demo? Yeah. Okay. Okay, I will do the demo. So so here's the interface. If we click the last module, we will see a very detailed interface how you're going to do two-sample Mendelian randomization. So you do not need to provide any input data. All the data is from the library we already collected. And you can see from earlier ones, we need to have the mGWAS, and we need to have GWAS. So the mGWAS we already collected, and GWAS is we obtained it from the OpenGWAS, and I don't think anybody is actually doing mGWAS yourself at the moment. So we just provided all the current mGWAS studies, allow you to select from the library. So this one is basically, you see from this side is all this job box. You can select one. If you're interested in certain metabolites, select it and put in the right-hand side. This is your metabolites. Then you need to find the phenotype. What's the phenotype you're interested in? Diabetes, obesity, kidney disease, cancer. It's about, I think, about 2,000 phenotypes. So you need to select one exposure and one phenotype. And here they will search the open GWAS and find the p-values from the GWAS, because mGWAS we already have it. And before we actually do the Causal analysis, next step we need to do some filtering or harmonization, just because there's a lot of SNPs going to be identified, both from mGWAS and GWAS. And some of them may be redundant, some of them may be actually on a different, the orientation or stuff. Overall, that doing the Mendelian randomization is well established in the genetic field. They have certain recommended practice to help you to reduce or enhance your SNP selection to do the Causal analysis. This part is we already coded into interface, and you have some flexibility to do that filtering. And I'm not going to do a very detailed intro, just because get to the bottom, you almost need to attend another several hours of Mendelian randomization and what each step means. But overall, this step is help to reduce the number of the SNPs and focus on the high quality ones. And the SNP here, we call it the instrument variable, because we use this to leverage SNPs to help us computing the Causal analysis. And this is a page I actually refer to, and we need to harmonize the SNPs and to be more suitable for Causal analysis. And this bottom actually shows what's the final SNPs you included. This is integrating both the mGWAS result. You see the mGWAS you selected from different studies, different stuff, and considering of the open GWAS we obtained. So this part you probably have a lot of SNPs and you don't want to have too many, and sometimes you can include and remove some of them. Especially study, if you are study from Chinese or Japanese, you want to include in the studies more close to your ethnicity, okay? African, European, probably not that suitable. But unfortunately, the majority of the mGWAS is from European. So this is something we realize probably future we have more mGWAS from the Japanese population will be more suitable. How do we do the actual computing? And there's a lot of methods. And we give you about 14 Mendelian randomization methods. And the default, here we shows about 5 of them. And you just select and move on. And how each method works. And there's the question marks. You can always find out how it works. And again, you're not a lot. You don't have to understand every method. It's just that people throughout the years developing every method for a certain niche application. They are not necessarily suitable for yours. So some of them is more robust. We select by default. Okay. And here it just shows about a summary result I showed you earlier. For example, here is called a forest plot. Forest plot basically tell you how the Causal effect using that each SNPs and how they contribute to the computing. And leave one out is try to reduce the SNPs and see how the result looks like. Sometimes you will find that certain SNPs have a huge influence on the result. And this is almost like quite commonly used for the robustness, whether it's susceptible to certain SNPs. Because I mentioned earlier, SNPs filtering will be important. If you accidentally include SNPs, it causes a huge drive your result, but the SNP is not suitable, and your result will be invalid. So in that case, you really have a very influential SNPs. You want to go back and double check that. And also here that shows how much correlate, because if the SNPs have p-values with GWAS and mGWAS, you want to see they are either positive or negative correlated, because you want to see that chain from genes to metabolites to the phenotypes more or less hold. So it need to have certain slope. And here's the final plot. Final plot, I don't have your very intuitive interpretation, but if it's not asymmetric and have something outlier, it suggests that you have some issues. They call it the horizontal pleiotropy. So it means something, and you need to go back to some filtering. So overall, that for us, metabolomics person do this is a lot of things feels overwhelming. But the thing that if you really found a metabolite associated with phenotype, you can always use these tools to try to see whether it's causally linked. Once it's causally linked, you can ask your colleague who is more familiar with this method, like genetics, to ask, is that okay, then we can double check and get the actual layer of confidence. So because this genetics manual randomization really recent one, even in their field, they have a lot of training workshops on this particular method. So do not feel, so you are not alone. So everybody is learning what's the best, but you can always use default method to quickly see what is worth the next step to talking to your colleagues to get to bottom every step things. If the causally linked, they really make a lot of sense. So here's a manual randomization result. It's basically, it's very standardized. So if you want to include it, here's the p-values, standard deviations, and exposures. And so if you use a lot of methods, some won't work because some methods are redesigned for specific situations. If you choose all of them, some will fail. So do not worry, that's okay. And hands-on time, oh, demo, okay. Demo, let's do demo. Do a demo, I can do a, oh, this is the main. Main is okay. I'll go to new or dev. Let's try the main. So main probably, oh, it's okay. You guys didn't overwhelm the server. So, let's go back. I mentioned here is statistical analysis. It is one factor. If you are uploading a sample, your sample contains one major, just one factor like control disease or stuff, then that's one factor. It's most experimental like this. If you study human subject clinical exposomics, and you really have multiple column of factors, some is primary, some is secondary, and you should use this one. So I'm just go through this. I probably go back, doing quickly, show you the PCA, PSDA. So, okay, I do a sample like the first one. So the first sample is urine sample, have two groups, cancer and control. And here is edited groups. If some group information is inaccurate or missing, you can just manually edit them. Here's missing value. Actually, I need to go back and find that missing value because this group this sample does not have missing value, so it's great. But if you have missing value, I think missing value. I cannot go there because there's no missing value. Let me go back. Maybe I can go to missing value here. Yeah. So here's missing value. We actually have a very common missing value. First, you remove the features with a lot of missing value because if you have half is missing, it's potentially low quality. You can remove them. And second is the default is replacing with the low detection of limit. Or you can exclude something or replace by the mean, median, or minimal, max. So whatever you want, it is allowed. Or you can use k-mean, k-nearest neighbors, or PCA or SVD. So there's a lot of well-established missing value imputation method you can use. But I just not sure how valid they are. I'm more or less comfortable with excluding or replaced by the low detection limit, because I think in a lot of things you don't detect it because it's low detection limit. But anything else statistical is possible, but how it impact result, I don't know. So this part is a very LCMS. We are talking about LCMS with some of the stuff. I don't know the statistics follow what we see from genomics or transcriptomics. Okay. Let's go back to the normalization. So I mentioned about a log transformation is the default. We should do it, but in this case, I think we do have some data have some systematic bias. So we just use normalized by the median or by the sum and log transformation. Let's see the result. Oh, I should see the result, maybe. Do it again, log transformation, median. So it looks okay. So you can go there. And here's a fold change t-test volcano plot. So I really suggest you to spend some time with things. We don't have a lot. You see, this is glucose, and you see some changes. This is low. I don't know which one's acetone. So you see fold change, t-test, very simple, but it's very effective for you. For example, here is defaulted FDR, and you use raw, and you have more. The thing is that we are not really concerned too much with strictly cut off. We want you to start think about data and think about biology. And so if nothing there, and because of p-values, FDRs, and basically that's not the goal. So you need to continue to explore and think about here. So volcano plot, ANOVA, PCA, PSD. So this is PCA. You see the PCA score plot, and so it's even t-test didn't give too many significant, but PCA looks nice actually. Cachexia control looks separating well, and the loading plot, something's wrong or didn't click. Okay, this is loading, and you can I think. You should be able to see the positive correlation, negative correlations with the things synchronized. You see this more or less the same thing with 2D, if you like this, but you should have sometime your 3D potentially relate to certain of the separations. Okay, and I don't know, they have this effect. You can see adding a little bit of this one. You see if you rotate in certain ways, you see the separation looks very nice. I'm just, we can actually swap between here, yeah, creatinine. Okay, so overall is the background, the white, black, sometimes join the view, score, background, the white. So yeah, so this is for you to explore. And PLSDA is probably most people are doing the PLSDA. And you see, oh, this one is not naturally improved too much because PCA already have good separation, and you need to do cross-validation. I think hopefully it's good. And the first component already gave relatively good, but the Q-square is not as what we hope. It's more than like 3.5, but this is what it is. Permutation, I mentioned the prediction accuracy. This is the one you mentioned, the prediction accuracy. This is the separation distance. So we can clearly do that. So if we're doing a permutation, it is 0.05 because we did 100 times. 5 out of 100 times, actually there are some random things is better than the original one. So let's go to 1,000 and see how it looks like. So 77 times, so it's 0.0077. So this is very empirical p-values. If you impute permuted result and how many times you get a better result, and this time basically divided by total number of permutation, and this is your empirical p-values. So p-value 0.077. So this is things. So I guess this is we have a lot of the other stats. So I'm not going to mention. I'm actually going to do quickly go this one. This is when you need to upload two data. One is your omics data, metabolomics. One is your metadata. Metadata is another table. So the first column is the sample name, and the second one is the primary metadata. So if you're not sure, always just open it, and you will download it and open from Excel, see how it's formatted. So I'm giving you the example. The first one is the COVID and the full metadata, but sometimes you have a lot of metadata. Yeah, a lot of metadata is, again, this is no missing value, since we just direct go through it. And here's the metadata editing. So you want to make sure all of the metadata is being recognized well. For example, diagnosis is categorical, gender categorical, treatment categorical, age is continuous. So default, actually, the computer gets it right. And of course, you can, if you click edit, you should be able to see what it looks like. Here's how you order them, okay? How you actually change it group-wise. So we spend a lot of effort to actually make sure you have the control to make the changes. And sometimes you don't want to exclude, you can remove them. And by default, everything looks fine. We just click, go through it. And here's the data filtering. And you need to remove some features. For example, variance filter, you removed features doesn't change a lot. And your abundant filter removes the features that low abundant. For example, here we just drag it to the left, is 0. So you do not want to filter anything based on abundance. And for the variance, you want to change, like, say, 30%. How about that? And I think for the reliability filter is based on QC. I don't think you can do it because you don't have QC samples here. I believe so, if I'm thinking. Here it will give you errors because there's no QC samples provided. So we just use one filtering. It's based on the variance. And basically, things doesn't change or doesn't change a lot. At the bottom, lowest, we are going to filter them out, like, say, 30%. So it removed about 600 peaks. This is on target. We're talking about, we have 6,000. So it's removed about 10%. Oh, that's 13%-ish. So now after we're cleaning things and we do the normalization, I mentioned about we just try the simplest first. And we do, like, see what it looks like. It's OK. And of course, you can always do experiment to see the difference. Normalization usually have a huge impact on the data. I just see it. But the thing is that usually have good biology, the separations, the story does not change. Even you see the PCA pattern change, but the story, the signal features, most very stable, okay? If some things change a lot based on normalization, you need to think carefully about what could be the reason behind it. So they will have effect, but they should not change the conclusion. That's the thing. So here's the method. We have a lot. And the first one I just mentioned about metadata visualization. This is very important because you need to identify those metadata actually similar. For example, here we only have 4 metadata factors, like treatment, age, diagnosis, gender. So for example, here, diagnosis and treatment is very related. This one is, like say, one value. This is the other value, basically treated or non-treated. And here is basically, this is diagnosis, this is treat, and almost highly correlated. There's something, not 100%, but you can see it's quite similar. The other one is age. So the treatment also, you see, are really with high age, probably more older. So a lot of the times you can actually have some feelings about how the metadata, how redundant they are, how related they are. And they actually here is give you some calculations which two factors actually highly correlated. And I think this is treatment versus diagnosis 0.754 and here. So it's very highly correlated. So it's not a surprise at all. And but if you have 20 different metadata, you really need to remove some of them. And another data, probably example data 3, will give you a much larger stuff. You'll find some very redundant metadata. You can remove them. And here is that we only have 4. You can keep all of them. But it really gives you some ideas about certain, how do you visualize it. Here's a PCA. It's also give you a good understanding of these separations. And here's basically try to coloring, and based on the, here's male, female, COVID, and healthy control. You can always color based on gender, age, treatment, and shape based on. So this one allow you to really overlay your metadata with different metadata. Okay, overlay the PCA data with different metadata, either by color or by the shape. Help you discover some patterns. This is all based on your visual inspection, and this is very important. And clearly, you can do some same thing with this. This is 3D, and 2D will give you more overview. And this kind of doodling actually helps some patterns. Sometimes it's very clear pattern will show up. If this clear patterns, and means that metadata actually influential on your omics data, that one need to be kept. At least when you do analysis, you need to pay attention to that metadata. Okay. And heat map, the same thing. We have a heat map, and you can see all the metadata here. And we have only 4, so it's really we can show everything just because it's very little. But when you have 20, that's a different story. And it will take a bit of time just because this is untargeted. We have thousands of features. And when you do that, see, this is a lot. But you do have a lot of controls. This one is you have font size, sample arrangement, and if you want to display top 15 and overview, detail view. So a lot of people actually quite like these features just because they allow you to go very detailed, and you can just zoom in actually. Here it didn't show, and you should be able to show the names, and you redo it. So allowed you to actually get very specific pattern where it is. And this is what I mentioned about the linear models. And you can do a statistical analysis considering multiple factors. And here is just ANOVA and covariant. For example, you consider age, and as covariant, and the primary is diagnosis, and you can do that. Now you will see the result. And here's significant features, 118.4, 18.2. And this significant when addressing it, sometimes became non-significant when you address it. So this is colored, this change. So when you address it, it became less significant. So all of this is you can actually click and see the patterns, and you will see something here. So especially when you do this, and here allow you to select the metadata. And if this one changes based on the covariant, you can actually choose the covariant, which one the covariant, see the patterns, and how it linked to it. Actually, it's a lot of times it make a lot of sense. Yeah, it's indeed correlated. When you adjust it, it's gone. The effect is gone. So here is a lot of the detailed inspections allow you to go from overview and actually go to individual, let's say individual features, how it affect. And again, is that you can go to very specific features and see where the p-values, t-scores, and adjust p-values, b-factors, and see the specifics. So all of this allow you to see that. So correlations, I ask random forest. So you do have the potentials to actually to do classifications and also consider metadata. For example, this is one diagnosis, and I think overall it's 0.186 is error rate, and this is, if we consider like say gender, will it improve? So it's 186.186. Consider gender will improve. I don't know. 169 and maybe improve. So sometime considering the metadata slightly improve. The things that they just put this metadata together combined with your metabolomic data. Before it's only you use metabolomic data. Now they can use gender to help improve it. How about we choose age? So you do not want to include the treatment because that you are cheating, because treatment is because of your diagnosis, okay? And in this case, gender and age is okay. I consider age, consider gender, and improves diagnosis. Let's see it will improve, okay? Yeah, 0.15, so slightly improve. I'm pretty sure if we include the treatment, it will have a huge impact. But it is nonsense, okay? Including treatment is nonsense here. Oh, not so much on. Let me see what's going on. I think in treatment should have a. No, okay. So I'm thinking is that because treatment is highly correlated and the including treatment should increase should decrease error rate, but it seems not so much. Anyway, this just shows you random forest actually can put the metadata together with the omics data to improve the stats. So if no questions, I'm going to move to the Causal analysis. I can do a demo for a certain method if you want. Okay. Okay, this is the last one, Causal analysis. This one is require no input from your side. And it is slightly wordy just because we know this is a new field to a lot. And if you see the intro, here's the Jiva studies here. If you click here, you will go to a new page and see every Jiva studies, okay? This is all the things we have collected. You actually can see some of this one result. So it's loading it. Hopefully it will be there. Majority is European, okay? I don't see, here is African, and this is a relatively large data, okay? I think this one's metabolon LCMS, so it's probably a large data set. Hopefully it's okay. Yeah, you'll see there's a lot of the significant features and here, and you can explore and how it looks like. But let's go back. So this is a GWAS study, MGWAS, and GWAS study we are going to get from OpenGWAS, okay? This is a remote database call. And what we usually do is that we just select one metabolite or one exposure. You can select up to 5, but once you select more than one, it's hard to interpret. So it's possible to do it, but just for the simplicity, focus on one thing at a time. Just select L-histidine, and we just choose like asthma, and we want to see how this one related to asthma, whether this exposure is causal or not. So I have no much background on this, okay? I'm just give a demo. And if you search other disease, make sure you start typing it. Actually, I'm going back. and going back. Do it one more time here. And for example, let's go to a diabetes. So should come out. So you're going to see diabetes. They have a lot of diabetes studies. And we just select one of them, type 2 diabetes from this. And hopefully this is a formal code. If you want to see more studies on this, you can search this code, you open GWAS. So we are using this GWAS study together with our MGWAS study result combined to perform 2-sample Mendelian randomization. And this time they will query the remote database and get the p-values from the GWAS. The p-value for MGWAS, we already have it locally. And once we have 2 p-values, we can do the stats, okay? Now here's SNPs. And let's see, we have a lot of SNPs, 13 of them. And they identify biofluid. All of them actually from one study. Oh, this is another study. And so have for 2 studies. And maybe we just exclude one studies and we leave them. And we also need to try to see if we can reduce it. LD clumping, as LD is linkage disequilibrium. So it's a common thing if they are inherited together, and you can merge them into just one representative called LD clumping. And proxies, and do not use proxies. So try to reinfer stuff horizontal, exclude SNPs that associate with multiple metabolites. So some of them, if some SNPs associated with multiple metabolites, and you can remove them, but in this case, we only have one metabolite, so it's not applicable. We just choose, like, say, do a clumping. You can choose use proxies to allow this one. Most time it doesn't have any effect. Let's see. We just use these common approaches, and you can read a bit on what is the effect, and then it started performing. We had been removed, one SNP had been removed using LD clumping, and nothing had been removed for horizontal pleiotropy. So more or less, we still have something. We have 7 left. This is after this. Now we clean our SNPs, and these SNPs will be used to do the 2-sample Mendelian randomization based on the GWAS and MGWAS p-values. And there's a lot of methods you can use. And here already default 5. And we just keep the default because that's... and you can always put your mouse over this different question mark to find more. But overall, it's, you're exploring just to try to... So this is a result we mentioned about, and it gives you some overall effect size. This is 0, so this is not very strong. Some of them have some high, some is low, and this leave one out. So leave one out means remove one, what's the change? Remove one, what's the change? This is the funnel plot, and it's a little bit funnel. Especially you have a lot of the SNPs, and the shape will showing up. Scatter plot, and you see this almost flat. There's no much slope. That means the coral is not that clear. Okay, the conclusion is not very. It's not very conclusive. You can see the effect size is close to 0, and you don't see a very strong positive negative. And all of this point to the similar conclusion. The coral analysis here is not very clear, so we don't know. And some of them, if you see the strong slope and see that effect size, you will find, wow, this compound is correlated associated with this. And you want to read more on the literature. And this time is, I just do a demo. I just randomly select the first methylhistidine, 1 diabetes. So it's like this is totally normal. If we found it's coral, I'll be very surprised. So it's nothing wrong with this approach. But I just shows the result. Seems not very conclusive. Because randomly, you don't want to hit some normal. So this is pretty much I want to show. It's if you want to try or ask some questions, or I can finish the last bit of the slides. We have 3.
I think you can finish the slides.
Okay.
We don't have too much time left.
Yeah. Okay. I guess more or less you guys following. You think it's okay, right? I'll finish all the remaining slides, and you can always do the practice later following the slides and post your question to the forum. Okay. And last few slides, demo. So summary and future perspectives. So roadmaps. So what's next? And people ask, hey, we have every 3 years new release, and the past 2 releases MS1, MS2. When I'm in a conference, people already mentioning, and I'm getting it. So we get MS1, MS2 finally there. But what's next? So from my point of view, is we want to do more close to multi-omics. I see we are coming, and with genomics, transcriptomics. And the other ones, what's next? What I'm personally interested in called the conversational analytics, which is we do not need too much web page. We just need to talk or need to normal language with AI. And the other ones, what we try to do is sustainability, because we after 12, 14 years, and it's very hard to get more funding to continue supporting this one. So we are actually trying to find new ways to support. And so we actually consciously we actually build a whole ecosystem of do omics data analysis. And today we're just talking about the MetaboAnalyst, but we have other tools for our transcriptomics and microbiome. And from this, actually, you get the list of signatures. You get normalized tables. You can actually do multi-omics, either using knowledge-based, data-independent, or become data-dependent or data-driven using some dimensionality reduction. So we build tools actually help to for all different omics can be used a consistent workflow to do data analysis and interpretation. And multi-omics very common. I get a lot of questions. But there's 2. You just think about how they're going to integrate. One is qualitative integration. Basically, you get signatures. You want to see from different omics and how they link together. And how we do it is we have networks. And basically, the networks, all the different molecules link together. And from metabolomics and proteomics, genes, SNPs, and even microbes, you project these significant features there, and you will try to link it and show up in the network. You can see how they link, potentially mechanistic, potentially data-driven, and help you interpret it. So it's a purely visual knowledge-driven, okay? And here's a quantitative analysis. You need to upload your normalized table, and they will try to use a common, well-established multi-omics approaches, such as dimensionality reduction and like PCA similar, but it's extended to multiple tables, like Diablo, MCIA. So there's a lot of the commonly used approaches, very robust, and you can do that and to do data analysis. So here's slightly more stats heavy, but we have very good visualization to help you to understand it. Just you need to be more patient, because it's a huge area of stats for multi-omics, especially in the this quantitative integration. So if you're interested in multi-omics, read our latest Nature protocol, a web-based multi-omics integrator using the Analyst suite tool. And so here the figure is actually doing knowledge-driven, but we have the data-driven, so more or less you should, the concept behind it is well explained. And here's we're talking about conversational analytics. What we are doing currently is more about visual analytics. We use cloud, we use visualization. So you interacting with the data and interacting through your browser. And we need to build the web pages so you can use it. And build that web page taking a lot of times. And what we're thinking is that also a lot of what you want to do is not supported through the web page, just because each web page is taking longer. But if you can talk, you can type and ask that to do it, you can do it. And before, I always think about it as chatbots about allowed to do it, but it's hard to do it until now with this generative AI, with this cheaper and cheaper, like a ChatGPT 4.0, it's very good already. And actually what we want to do is that you can talk to the chatbot. Actually, they will help you to do the data analysis. We already have the workflow built in, so you know it's built in. It's underneath that. So it can run the workflow for you. It can build a report for you, and it can build if you are interested in underneath, you can click all the way to the lowest point. Here we show is actually this is a functional analysis from Mamichog we showed you earlier, but this is in a dark mode, okay? So it is, and also another thing, in addition to data analysis, the other one is writing your manuscript. So not necessarily manuscript, but it's close to more beyond the analysis report. Analysis report is very dry about your data, but if you give it more background, literature, like I writing a paper, I usually read about 20 different papers more recently. You can actually together with the analysis report, together with your feature, and it will help you write your intro, potentially conclusion part. It actually understand very well to help you do that. So a lot of this is actually very useful to help us to save our time. So I know some people are already using this, and so I would like to really imbue this into helping us to write. And writing paper take me about 2 or 3 weeks. If we bake in 2 or 3 days or 1 week, and already significant. Usually to at least accelerate, at least one, you should be reduce your time by 1, yeah, quite a lot. So it is clear there. And so this is part is, at the beginning I mentioned about we have the training. The other part is we're talking about pro version. So we start offering the pro version. And all the features about AIs, even different features. And we have pro version. So this pro version is really, you can see here is we have project management, workflow creation, resumable analysis, and report, and AI. So AI is experimental, not available yet because we are not fully comfortable. But most everything else is already there. And a lot of people want to do raw data processing. We said we cannot support everything else, but if you are doing a pro version, there's a lot of the features, upload data, and you can analyzing a lot of the features almost in the back end. So project workflow, this is because you are going to have a subscription, you're going to have an account. So it will be there as long as it's active. So you can always reanalyze and again and again. So this is something we are doing, so to help sustain the tools. And so this is final. So if you have questions, do the stuff and create an account and post on forum. I'll try to answer it. And also you can send the emails, me and Zhiqiang. And also you're interested in general omics data science beyond metabolomics. We do have the omics data science course in the summer boot camp in August. And the regular session is in basically 3 months, every weekend. And because all of us have a full-time job, but we do it during the weekend. And it's all virtual through the Zoom. And we just had 1 session. It's everybody just love it. So this is the 2 coming sessions if you would like to do it, and it's still open. And that's it. Thank you.
I think we still have 10 minutes. So within these 10 minutes, you can try to practice what Jeff has introduced. And both me and Jeff will work around. And if you are also really interested in the pro versions and IEI stuff, welcome to talk to us. We will be here until 6:30. Thank you.